for this circuit that involve two diodes that are equivalent, like so diode 1 and diode 2 equivalent. Excuse me. So the characteristic of this diode kind of will look like this, and so this is the diode is going to be off, and here the diode is going to be on, and then the voltage here, the knee voltage there, which is the VD on. So when the diode is on, the current to the diode is positive, and the voltage across the diode is going to be VD on. The voltage across the diode is VD on. So we can effectively replace the diode by constant voltage source. The current is ID and the voltage is VD on. So now that we have two diodes, the analysis is we're going to approach it a little differently. So we don't know when diode one, the D1 is on, or when D2 is on, or vice versa. So when we wanted to analyze a circuit that involve multiple diodes, what we're going to do is to assume that one of the diode is on, and assume the other one is off, and then go through all the cases. So because we have two diodes, that means we have 4 cases to go through. All right, so one, I will assume that D1 is on and D2 is off. So D1 is on, that means ID1 will be positive, and the current through the diode ID2 will be 0. Okay, so I can redraw the network. So I'm assuming that the input voltage is a sine wave, right? So I'm gonna use a sine wave as input. So I have this sine wave, the input voltage VI. So over one cycle. So we have VI, then I have the resistor, and then we said that diode 1 is on, so I will have VD on, and the current ID1, call it ID1, and then the bias voltage V1 is there. So, and the diode number 2, D2 is off, but we have the second bias V2, bias voltage V2 there, V2, and the voltage across here, which is the output voltage that we're trying to solve for. So I can write KVL and going through this loop. So we have the voltage here will be VR. So VI will be equal to VR plus VD on plus V1. So VR is ID1 plus VD on plus V1. So this implies that RID1 is equal to VI minus VD on minus V1, and we know that D1 diode D1 is on, so ID1 is positive. This implies that VI is bigger than VD on plus V1. So under this condition, V0, so V0 then equals to VD on plus V1. So we recap the first case. We have V0 equal to VD on plus V1 when VI is bigger than VD on plus V1. So we have that. Now so number 2, we assume that D1 is off and D2 is on. So that means ID2 will be positive. So when I redraw the network, I have here, so diode D1 is off, so V1, and then so the diode D2 is pointing up, so we have this, and the V2 is minus and plus, that's V2, and the current ID2. So I'll still write my KVL. So that means the current ID2 is flowing that way. So I can write VR like that. So, and the voltage V0 is there, which is equal to negative, so that's VD on, so negative VD on minus V2. And then when I write KVL, I have VI, so let me write it here, VI equal to minus VR minus VD on minus V2. Now VR equal to RID2 based on the polarity that I have on the screen there, so minus RID2 minus VD on minus V2. So RID2 equal to minus VI minus VD on minus V2. So D2 on, this implies that ID2 is positive. So in that case, minus VI minus VI minus VD on minus V2 must be positive. So that means VI is less than okay, so I can just multiply this equation by minus, so VI plus VD on, going to avoid sign mistake. So VI is less than minus VD on minus V2. So for this case, so D1 off, D2 on, we have V0 got minus VD on minus V2, and VI must be less than minus VD on minus V2. So that is the second one. So case number 3. So when you have both diode on, so assume D1 on, so let's see what's gonna happen, and D2 on. Let's see if this case is going to be satisfied. So that means ID1 must be positive for this case, and ID2 must be also positive. Now let's draw our network. So we have VI, so the resistor is still there, so I can put the polarity of V like this, and then so the diode 1 is plus minus, so VD on plus minus the bias voltage V1. So make sure that I draw it correctly, and then for the second one, diode D2 is like this, and the bias voltage V2, the polarity that's given to us is V2, like that, and VD on now. The current to diode D1, ID1 will be there, and ID2 will be flowing up. Now those are the conditions, right? So ID1 and ID2 will be positive. So now I'm going to write KVL around this loop to see if this condition can be met. So starting from the bottom, I have negative V1 minus VD on, and then minus VD on, and minus V2. That is equal to 0. So that meant V1 plus 2 VD on plus V2 equal to 0. Now V1, the bias voltages V1 and V2 are positive voltages. So this, right, so V1 is positive, V2 is positive, right? So that means the sum, this equal to 0, is not possible. Not possible. That means both diodes cannot be on at the same time. At the same time. So when the bias voltage is V1 is positive and V2 is positive. So I should probably indicate that at the beginning. That was the assumption. Okay, so then so when the last condition is D1 off and D2 off. So in that case, what do we have? We have this resistor there. So I have the resistor there, and the diodes also, all this is open. So this is open, V1, and this is also open, so V2. The voltage here is V0. So in this case, there is no voltage drop across the resistor. So Vi, which is equal to times 0 plus V0. So V0 is equal to Vi when both diodes are off. So when we put it all together, so V0 will be equal to the first one, which is VD1 plus V1. So let me just copy that over there. So I'm gonna paste it here. I'm gonna shrink it down. So that's the condition number 1. So that's D1 on, D2 off. The second condition is this. So paste it here. So for this case, okay, V0 when D1 off, D2 on, and then the last condition is V0 equal Vi. That is number 4. So D1 off and D2 off, and that middle condition, which is not possible. So I have all my output voltage for each case. Now I can sketch the output voltage, the transfer characteristic. Okay, so let me sketch as we have been doing it. Sketch the output voltage and the input voltage, and then the transfer characteristic. So let's say this is a V1, so this is VI, that's V0. So we have V1 plus VD1, okay, so minus V2 minus VD1. So it's the same thing here. V1 plus VD1 and minus V2 plus VD1. So now when V1 is bigger than when VI is bigger than VD1 plus V1, V0 equal to this. Okay, then when it's VI is less than V, so maybe I should move the graph a little to the right. And so then it's easy to sketch. Now when VI is less than minus VD1 minus V2, then there, so it's going to be VI will be this, and then so between these two is going to be, so the condition will be V, let me put it small, so minus VD on minus V2 less than VI less than VD1 plus V1. So that will be equal to 1. So slope 1. And so when I sketch it, it'll look like, oh, that's too big. That is too big. So maybe this. And this. Right. So that is a transfer characteristic. That's the transfer characteristic. So V out as a function of V in. Okay, but if you're asked to sketch the input voltage on top of the output voltage and the input voltage in the same graph, so let's put that. So this is T, so this is Vn, so let me sketch Vn. Sketch Vn. Now we have V1 plus VD on, So minus V2 minus VD1. See the analysis, right? If anything changes, going through the same process and you are going to get the same result. Okay, so between the two, the voltages are equal, right? So VI equal to V0, right? When we're here, right? Between the two. Okay, now when it's VI is bigger than VD1 plus V1, then it's gonna clip, and it's going to clip. So we have this, and then it's going to clip. Okay, so this is a limiting circuit. Okay,